Welcome to our tutorial today. Hello fellow enthusiasts, welcome to today's tutorial. Let's join in and do these practicals, and then we're gonna wrap it up at the end. I'm gonna show you a few tutorials, and then we go and we have a demonstration. We're gonna have a demonstration. So let's see, let's make sure that we are live. Let's make sure we are live. View channel. Okay, we are live, all right. So we are live. Yeah, we are live. I'm gonna just test the audio. Are we live? Can we be heard? Demonstration. All right. Yeah, so we can be heard. So we're gonna go and do this demo. We're gonna do the tutorial and then the demo. The first thing we're gonna do, I'm gonna establish what the tutorial today is gonna be. Today is gonna be about DC to DC power supply. You know, when I worked at BlackBerry a few years ago, several years actually, I walked into the interview and one of the panelists asked me a question. He said, your phone has a battery of about 3.7 volts, and sometimes you will generate, you need to generate up to 2 watts to transmit a signal, depending on where the location of the mast is, the closest mast is. And then the antenna resistance is about 50 ohms. And he was asking me, how do you generate this amount of power from 3.7 volts? So we're going to do a math together. I'm not going to make any assumptions. We're going to do math together. We know that power is IV, current times voltage. And they didn't tell me the rating of the current rating of the battery, so we have to make an assumption, and we know that from Ohm's law, V is equal to IR. And so since I didn't know I, but I know V and I know the power, I can eliminate what I don't know. I know I don't know I, so I can make I the subject of the formula, so that I is equal to V over R. And so I can come to the equation of power and I substitute I and replace it with V. So it's going to be V over R, that's my I, times another V, such that power is equal to V squared over R. And so I know that my power already is 2 watts. So 2 is equal to V squared over 10, over 50, sorry, R is 50, over 50. So that my V squared is 100, and that means that V is square root of 100, which is 10. Did I get the math correct? Sorry, I'm not solving for V here. What am I solving for? Yeah, I'm solving for V too. Yeah. Okay. So this is what the math we did. So the voltage is 10 volts that I need to generate 2 watts of power. I need 10 volts to generate 2 watts of power. But how do I get 10 volts from 3.7 volts? That was a problem. So let's go through the math again. I'm just doing it right now so we don't make mistakes. Let's move this away. So maybe we should do it again, just to be sure. So V is equal to IR. First of all, power is IV. right? So I was given the V, I was given the I, the P. I could actually calculate my I by saying that I is equal to P over V, right? And power is 2 watts, and V is 3.7. I can do this and then calculate I. And then I will say to you the I will need to generate my power is XYZ. So the battery must be able to supply that amount of current. So that means I'll require around 541 approximately milliamps for my battery to produce that amount of power. But they were asking me to solve this problem without resorting to finding out what the current is. So what I need to do is to figure out what voltage I need, so I was given the voltage. The voltage is 3.7. I was given the resistance, which is 50 ohms. I was given the wattage, which is 2. And I was asked to figure out how this battery, without figuring out the current, but how this battery will be able to generate the amount of voltage to give me the amount of power. So we walked through what we did earlier. We said P is equal to IV, which is equal to, since I is V over R times another V, is equal to V squared over R. And I know that R is 50, so P is 2 times 50 is equal to V squared, such that V alone is square root of 100, which is 10. So the question was, how do you get 10 volts from 3.7 volts? So it was my first day. I wasn't so sure how they do it, but I told the guy that you can do DC to DC conversion. You can up convert the voltage from here to 10 volts. And it was okay. He was happy that I knew the answer, but what I didn't know then was how to generate that DC to DC converter in a simplistic form. I've built inverters before, so in my mind, I will build an oscillator. I like block diagrams. I'll build an oscillator, power it with the power supply they gave me, 3.7 volts. So I'm going to build a 3.7 volts inverter. And then, but this, my oscillator will have a transformer, a step-up transformer. So this, my step-up transformer, will then go through a bridge rectifier or any form of rectifier. For simplicity, let's just do simple rectifier. And then I would have, since I need it to be 10 volts, I would have to include a Zener diode somewhere. So maybe I have a resistor here, then a Zener diode here, and this Zener diode will be 10 volts Zener, and then I have my 10 volts here. You know, everything I did, it was kind of acceptable at the time, but that's a longer way to go because this oscillator requires me, or this oscillator here will require me to use 2 transistors to generate a stable multivibrator, or to use 555 timer to generate the frequency, the pulse width modulation, and then I'll have a transformer, and then I have all these other components. So that's how you can do that. But over time, when I built Joule Thief, I was able to figure out how these things will work in a very simple way, and that is what we're going to learn today. All right. So how do we do this? In an easy way. We know that an inductor stores electrical current. Likewise, a capacitor. But let's just deal with inductor right now. If I supply a DC voltage to this, there'll be a surge, but then it won't last, because these inductors, they oppose DC voltage, right? So you know that capacitive inductance, or inductive reactance, which is XL, is equals to 2 pi FL. So let's figure out if my statement was correct or wrong. We can correct it. 2 pi FL. So if L is 0, then XL is 0. So really there's no reactance at DC voltage. So this will not offer any reactance, any resistance for DC voltage. So I was wrong. So this is the correct statement. So if F is 0, frequency is 0, then your XL is 0, right? So the entire voltage will flow through this. But then if this fluctuates, when it becomes AC, then F is no longer 0, is a non-zero value. If F is a non-zero value, then the XL will have a value. The reactance will have a value. So let me show you what I mean. If I put a switch here to ground, and I put a voltage here, say positive supply, when the voltage flows through this inductor to ground, it will store electrical energy. When I break this circuit, that electrical energy stored will be discharged. It will dissipate somewhere, will go somewhere. So when current flows through an inductor or a conductor, it will store magnetic energy. It will store magnetic energy. When the source of that electrical energy is taken away, that magnetic energy will dissipate, will dissolve back into the conductor. And when there's a change in magnetic field around the conductor, it will induce voltage, electrical energy. So electrical energy will generate magnetic energy or magnetic field. The magnetic field will generate electrical energy, and vice versa. That electrical energy generated could be as high as anything, as little as anything. But sometimes it could be so high that it might burn off your switch. So what we do then is to put a diode across the switch to create a flyback effect, or to prevent inductive kickback. So if I have a diode like this, then when I remove this source of electricity here, instead of burning off my contacts, the current that is generated in this conductor will go through this and go to the ground, go through the diode and ground. And so I'm going to show you how we use this theory, this phenomenon, to generate a DC to DC converter. So what you're going to do is, if I have an inductor, I'm going to have a diode here, and in the middle of this diode and inductor, I'm going to have my switch. So I'm going to just put a switch, and then I'm going to ground it. Here I'll put my positive voltage, and here, because I need to make this portion useful, the output circuit useful, I'm going to put a capacitor for filtering, a filtering capacitor here. Ensure that the voltage of the capacitor can handle the voltage that is going to come in here. And then I'm going to have my load. So I'm just going to represent my load with a resistor. Right, so this is my L1, inductor 1. This is my D1, diode 1. This is my C1, capacitor 1. And this one, I can call it my R1 now, because I have no R in the circuit, R1, which is my load. Now what's going to happen is, when I close the switch, there's going to be current flow through here to ground. When I open the switch, remember my battery is on this side. When I open the switch, there'll be voltage generated here that will dissipate. But now the switch is open, and it will go through this diode to my output circuit. The capacitor will filter it, and then it will go to my load. So this is how you create a DC to DC converter, because you're gonna have a DC power supply here at the input, and you're gonna have DC at the output, using a resistor, using a diode capacitor combination to create the filtering, the rectification and filtering circuit. So this one here is a rectifier, and this one is a filter. So that's how you create your DC to DC converter. Now, you need this to be switched at a very high frequency. So you're not going to put your hand in your circuit and be switching it up, down, on, off, on, off. No, you're not going to do that. So here is where we're going to use other components to generate a switch, to act as a switch. Now, we've worked on something we called transistor switch before. So we're going to use similar thing right now to create DC to DC converter. In this case, you can use a transistor. Any transistor can do, but you make sure that the frequency that switches it can handle that the frequency, right? You're going to use a very high frequency switch here. However, we're going to use MOSFET today instead of ordinary transistor. Why? Because we want to be able to control the pulse width a little bit, and transistors, MOSFETs, do better than regular bipolar transistors. So we're going to use transistors, MOSFET transistors. The gate resistance is very low, and then it can handle very fast switching system. It can handle sink more current or source more current than many regular transistors. So we're going to use a MOSFET today. There are many other reasons why you're going to use MOSFET. Speed, one of them. Low RD on. So RD resistance of the drain to source, RDS resistance, very low, so that you don't lose a lot of power in the transistor or in the MOSFET. So you have low RDS resistance of the drain to source is very low. When it is on, RDS on, when it is on, this is very low. All right, so that's why we're going to use a MOSFET. Let me now redraw the circuit and replace this switch with a MOSFET. You have a space here to do that. So remember, you just need an inductor, you need a diode, you need a capacitor, you need a load. So this load, we can leave it for now because we can just add, we can use a multimeter to measure the output. Oh, speaking about multimeter, we need battery for our multimeter. So let's see what we're gonna do before we do that. We need a battery, or maybe we can use an oscilloscope. Oh, small oscilloscope. Where is the oscilloscope? Forgot to get battery before this project. All right, let's finish this and then we go get battery for the multimeter. So here we're gonna use a MOSFET. So you're just gonna connect it like this, and then so you're gonna use N channel MOSFET. All right, so that's the switch. And then the pulse, so let's just give it, we're going to put two resistors here. Okay, I didn't draw this gate properly. Anyways, but you get the point. And then I'm going to use another resistor, which is, so this one will go to ground. I'm going to use another resistor to ground here. Now what I will draw this bigger, I'll draw it bigger. So I'm going to use pulse width modulation here, the gate resistor, and then there's gate to ground. This one here pulls it down so that when there's no pulse here, the gate is grounded. So I'm going to need that resistor. It can be 10K, you can use 10 kilo ohms and above. And for this one here, I can use maybe 220 ohms, something like that. And my positive supply goes here. This is ground. And that's my D1, L1. This is my switch now. I'm going to call, so this one, initially we called it switch 1, right? Now it's going to be, let's say Q1, which is because the transistor. And then this remains our C1. This won't be R1 anymore. So let's change the designation from R1 to RL so that it retains the designation. And then this guy here becomes R1. And then it's on R2. Alright, so this is the circuit we're going to build it right now. We're going to build it. So we're going to build it on this board. I'm going to build it on this board to hold everything. Then we're going to use one of these inductors. Alright. I don't know the value of this inductor, so we're going to find out. We're going to use this inductor, or one of them. We have multiple inductors. We're going to just use one of them. Alright, and then we need a MOSFET for the switch. Alright, so we're going to need a diode as well. We'll use a fast switching diode. This one here is a UF, oh, these are not ultra fast, UF 407, ultra fast. Can you see that? Alright, so that's it there. Ultra fast recovery diode, that's what we're going to use. So just going to take one of them. Alright. And we need a MOSFET. MOSFET, where are you? So let's get the MOSFET. We're going to need some resistors. So we're going to arrange all the components before we start soldering. So we go in one swoop. So here are the resistors. Are we going to look for 10K, 10 kilo ohm, or what did we say here, 10, yeah? So the color code for that, so 10 kilo ohms is going to be brown, black, orange. Brown, black, orange. That would be 10 kilo ohms. Now if you don't know how to know the value of a resistor, you can go to our basic electronics tutorial to learn how to find the color codes of a resistor. Now this 10K doesn't have to be exactly 10K. We don't have to spend so much time looking for it. We can use another value higher than 10K, which should be fine as well. So 120K is not bad. 220K is fine. 10M is also fine. 2M is fine. We have so many options to choose from, but I'm just going to look for 10K. If I don't see, then we can use a higher one. 270K, 2M, a lot of 2Ms. 80K, we have 80K. 150K, lots of them. 390K. Alright, so these are very high Ks. Let's try this partition here. 200K is here too. Alright, 1K5. Okay, I think we're closer. 20K. Let's do 20K. So we can use 20K. 20K will be red, black, orange. So let's see if we can see the color. I'm going to try to make it closer. So let's do 20K there. And then we need around 20 ohms, 220 ohms, anything little can do. I have 20 ohms here, but let me see if I can get let me see if I can get up to 100K, 100 ohms. I see 120 ohms. I see, yeah. What is this value? This guy is 820. A little bit too high. 56K should be in this batch. 560 ohms. Okay, 12 ohms. Alright, I'm gonna do 20 ohms. Let's just do 20 ohms. It's 20 ohms, yeah. This guy is 20 ohms, so we're gonna use it 20 ohms here. So we still don't have our MOSFET. So let's go find a MOSFET that we're gonna use. So I think this is a MOSFET, yeah. Okay, this is IRF 840. Let's see if we can zoom in so we can see the component we're using. So that's IRF 840 MOSFET. We're going to take one of them. This guy here is the UF ultra fast switching diode, and here we have a resistor. It's blood. Okay, you have to just agree with me when I tell you the color. Just believe me. Is brown. Sorry, this is red. Red, black, orange. Just believe me, it's red, black, orange. Let's see if we can magnify it a little bit, if it helps. Alright, let's see. Yeah, you can see it. It's red, black, orange. Believe that. Red is 2, black is 0, orange in the third band is 3 zeros, or times 10 raised to the power 3. This one here, I need to find, yeah, okay. You can see that. Red, black, black. So right there, red, black, black is, red is 2, black is 0 in the second band, but black in the third band is a decimal multiplier, which is basically 10 raised to the power 0, which is 1. So 2 times 2 plus 2 0 times 1, that's 20. Believe that, that's what it is. Alright. Now we're gonna measure the values of the inductors, because we want to pick one of them. You're gonna pick one of them. So where's my inductance meter? Alright, we need our inductance meter. Where is it? It's not here. where's the inductance meter? Alright, I haven't seen the inductance meter, but I have the oscilloscope, tiny one. We're going to use that at some point. But we need to first of all measure the inductance of the inductor we want to use so we can calibrate properly. But without the inductance meter, I think we can still go ahead. We need to find it because it needs to be in its place. Everything has a place and everything should be in its place. But that's not the case right now. So we need to find it. Right, let's see. Did we put it away in the bag? Alright, that's strange. We can continue with that inductance meter, but that's just strange not to have the inductance meter. We had to clear this table for this demo, and so we'll probably put it away when we're trying to create space. I'm gonna need a heatsink for the MOSFET. We have bigger heatsink like this. If you're gonna use a lot of power, you require a bigger heatsink. But let's just build this demo and we can figure the rest of things out later. Alright, I couldn't just let it go, so I have to go find the inductance meter because I want to show you how to check certain things, and we can't just let it go like that. So we're going to put on the inductance meter. This is the inductance capacitance meter. Are we at the right height? Let's see. Yeah. Alright, I'm just going to get some probes to put in here to run our tests. So I'm gonna use some of these probes. So let's use this one. So red to red, black to black. And then we're just gonna connect. Take one of the inductors, clip it here. Well, first of all, I want to calibrate. So I'm gonna calibrate. And then, so I'll zero it by, just press it, zero it out. Alright. Yeah. And then I'm gonna connect it. This is 20 microhenry. Let me try another one. This is 320 microhenry. Okay. I want to use something around 100. So let's see. Around 100 microhenry, between 100 and 200. 46 microhenry. 18 microhenry. I don't know if you can see that properly. You don't need to see me make any connection. You already know how to do that. I'm just gonna read together. 18 microhenry, not good enough. It's not bad, it's just that I want to use something a little bit more. But if we don't see, then we can manage. 313 microhenry. And the last but not the least, okay, I have another one that we made by hand. We're gonna test all of them. This one was purchased. And this is 46. Well, I didn't see the 100 I was looking for, so I'm probably gonna use 46 now. Let's try. This one is 20, I think. Yeah, 20 microhenry. This one done some time ago for Joel Thief. We're probably gonna repeat this project. But let's see how much inductance we have here. What? 340 microhenry. Okay, how about the center tap? 86 microhenry. Each side is 86, but the entire thing is 300. How does this work? Anyways, okay, whoa. I didn't know that we got this amount of inductance. Okay, so we're gonna use this one that is 46. Just confirming it one more time. 46. Yeah, 46, 47 microhenry. So we're gonna put the rest away so we don't lose them. And we gotta put them in the same place where we got them from. That way, when we need them again, we will find them. Now I put away the container. And now I am just gonna put it right there. Okay, all right. So we're done with the meter. So you can go and take some rests. Keep it back at the same place we got it. The next thing is to fire up the soldering iron. So I'm gonna get out one MOSFET, but before I touch the MOSFET by hand, I'm gonna try to discharge any static electricity on my palm by touching heavy metal. So my workstation is made mostly of metal, so I'm just going to touch it to discharge any static charges, especially in the cold. This is a winter season, so touch metals to discharge your fingers. And then I'm just going to open and take one of the MOSFETs out. I'm going to need just one of them. And then I'm going to return it to the source so we don't look for them. So let's see. We have a diode. Where's my diode? We have a diode. Check. We have a MOSFET. Check. We have the 20 ohms. Check. We have the 10 kilo. Not really the same value, but check. We need a capacitor. We need a capacitor. We can take a very big one. This one we're going to repurpose. It was used before. This is 25 volts. 3,300 microfarads. this might be too small for what we want to try. We want to generate a lot of voltage. But we can actually control how much voltage we're going to generate. Let me see if I can get a bigger one. If I can get a bigger one, then we can go higher. When I say bigger one in terms of voltage rating, let's see if we can get higher one in terms of voltage rating. Alright, what are the capacitors? Same 25 volts. Alright, so that's not high enough, or it's same rating, so we didn't satisfy the purpose for looking for another one. Alright, I guess we're gonna just limit ourselves to 25 volts today. But I was gonna go a little bit crazy in terms of how high we could go. But it seems it's not gonna happen right now. Where are my capacitors? Let's go to the trove, see if we can find something. Not in this trove. No, not in this trove. We have other capacitors, but these are resistors actually. We have other capacitors, but they're not in this trove here. How about this trove that has been out here for a while? Let's try this one here. Okay, we have many more capacitors here, but they're very tiny. Let's see this one here. $25 volts again. So it seems we have lots of 25 volts capacitors. Not as high as I wanted. These are very tiny ones. Okay. Let's try this one here. This one is so small to see the value. This is 16 volts, even smaller. Alright, so let's just limit ourselves. Let's limit ourselves to 25 volts. So we're going to be very careful when we build this. And I'll explain to you why I'm looking for this. Because the output might go very high depending on the pulse width of the PWM. All right, let's start. The first thing I'm going to do is to secure my MOSFET. I'm going to secure the MOSFET. Let's go closer. We'll need to adjust the camera a little bit. Okay, how do we do this? Alright, let's adjust it a little bit so we can come inside a little bit. Alright, MOSFET. Yeah, IRF 840. So that's what we're going to use. And then I'm going to add a heatsink to that. So I'm going to use one heatsink. This heatsink here I'm going to use. And I don't need to use the insulator because it's just one. I normally would use the insulator if I'm trying to create isolation so there's no short circuit, something like that. I don't have to use this, but I'll just use it to show you how it's used. And then I need a screw. Where's my screw? Alright, so I'm gonna need this one. I think that's it. Then I'm gonna put the rest back to the source. So we're gonna look for it again. Alright, now I want to make sure that the heat is transferred accurately. So I'm gonna use this so I'm gonna use a thermal conductive paste on it just to help me make sure that heat is transferred accurately. So let me show you what I mean. So I have a thermal conductive paste that I'm gonna use. It's thermal conductive paste. I'm gonna just put a little bit at the back of the MOSFET. Push it through. That way the heat will transfer easily and efficiently. Yeah, just put it here. Again, seriously, I don't need this insulator, but I'm just gonna use it for the sake of it. And I'm gonna put the MOSFET on it. And I put the insulator. Really? I'm just gonna ask myself one question. Why are you putting all this? Because you don't really need them. And that's it there. So I'm just gonna get a screwdriver to drive it down. Alright, screwdriver. Might be too big. No, it's not. have to make sure it's lined up properly. All right. It's done. Then we're gonna just insert it through our board. And it's right there. Now, the MOSFET has 3 pins. So let's draw it. So this is IRF 840. So it has 3 pins. And now what we're going to do now is to figure out which pin is what. Remember, there's the gate, drain, and the source. So which one is our gate, which one is our drain, and which one is our source? That's what we're going to figure out now. And how we're going to connect them together. So some of them, I think most of them, they have the similar pinout, but you can check on the internet to figure out the one you're using, what does the pinout look like, right? You can use a different one. You don't have to use the exact one we're using here, but you can figure out what the pin is. The first pin is the gate. That's this one here. This pin here is the gate. Where's my drawing is not showing properly. Yeah, that's the gate. This one here, which is the first one. Okay, I think I have to zoom out a little bit because I'm too close. Okay. Yeah, and then the middle one is the drain. And then the last one is the source. So gate, drain, source. So in this format then, here's your drain. It's almost like your collector. Then here's your source. Since there are 3, if you know 2, you know the other one. The middle one is the gate. So that's how we're going to work on this right now. We're going to solder it in that order: gate, drain, source. Put the 2 resistors to the gate, then the inductor, the diode, the capacitor, and then we'll test our system now. We're going to have a little bit challenge because we need to provide the pulse width modulation. But for that, we're going to program an Arduino, maybe Arduino Nano, pulse width modulation. We're going to program one, or Arduino Uno. We're going to program one to provide that modulation for us. All right, so let's do that quickly. Let's do the soldering first. So now I'm going to be very careful with my setup here because I'm going to turn on the soldering iron. So I'm going to move things away from the path so we don't screw up anything. So I'm going to clear this first. And maybe what I'm going to do today is after soldering we can call it a day, and then another day we do the programming so this doesn't become too long. All right, so let's do that. Let's do the soldering first. And then bring this to the center, and I'm going to turn it on. So there's a switch here for my soldering iron. Let's move away a little bit. Okay, that's the maximum we can go. Turn it on. We'll set the temperature. It's just gonna climb gradually, and then we'll be back. And we are back. It should be hot enough right now. It doesn't take time to heat up. It doesn't take time to heat up, so we're back now. So let's, yeah, it's hot. It is hot. It's hot. So we're gonna test it by using our lead. We have a soldering lead. To be able to solder, we need a lead. Okay, right there. That's the soldering lead. That is soldering iron. And we're going to use a cleaner to clean the bit, the solder bit, so we can have smooth work. Alright, so we can use anything to clean it, but we have a wire mesh. So let's go get it so we can clean it. Right. So gate, drain, source. Gate, drain, source. So source is, so I think I'm going to turn it this way. So the source points downwards. Doesn't, not that it means anything. And then gate is top. Drain is the middle. Sometimes I wish that the is different. Okay, let me just turn it sideways. I'll put it sideways. That way I can bend the pin the way I want it. The first one is gate. So I can bend it outwards this way. And then the drain is the center. I'm going to bend it up. And then the source, I'm going to bend it down. You can see the way I did it. And now I'm just going to put it here. Alright, I need to make it a little bit tighter. Not tight enough. All right. Okay, let's just do the soldering. There's no point leaving it on for a long time because it heats up quickly, so we can always turn it on when we need it. Now the inductor is from the positive and ends up at the drain. So the drain is the pin that goes up. So it ends up at the drain, which is this pin that comes up. So we're going to put the capacitor there. I'm going to try to make sure it doesn't touch so that if it's heating up, there's no issue there, just in case. So I'm going to turn it backwards. All right. Alright, I've done this one here. And power supply go backwards. Alright, and then on the same pin, I'm going to have my diode. So the diode starts from the same drain. And the anode is the one that is connecting to the drain. And the cathode is going to my... So I'm just going to put it on the line. I like to make things look beautiful. Okay, so let's do that. Okay. Right. I just remember my friend Itumafo right now. If he's doing this, it will be very compact. Very beautiful. Oh, I don't get as compact as he does. Alright, I need a cutter. I need a cutter to cut off the excess leads. So let's get a cutter for the leads. And the cutter was always with us all along. And we're just looking for it. So I'm going to use the nail cutter to get it off. Alright. So let's go back and do a little bit of soldering. I don't have to do as often as I'm doing, just... Okay, now we have to turn it on to heat up. So in the meantime, we can connect the resistors. The resistors, this one here is the 20K. So you can put the 20K. And then the 20K goes from gate to ground. So gate is the first pin. So 20K goes from gate to ground. Alright. And then we're gonna do the 20 ohms goes from the same gate but it's now gonna go to the input. So what I'm gonna do is to make it line up beautifully, I'm gonna line it up on the side. Right, 20. Alright. And then I'm gonna line this one up from the same spot. All right. Okay, now I can solder. I'm gonna make it a little bit thick to be able to handle a lot of current. Alright, I think that's it. We're almost done. We're getting there, we're almost done. So we're just gonna include the capacitor. This is really too much. 3,325 volts. Let me see if I can get a smaller one. No, we're not gonna. Let's see. Have to observe the polarity too. This side is the negative, so we're gonna just install it. Right, so it's not going through easily. There are some LEDs left over on the pins when you were removed from another board. I think we can actually test the inductance, the capacitance. Let's test the capacitance before we continue. So capacitance, I'm gonna just alright, capacitance, it's a high value. Let's see. 3 millifarad. Yeah, which is the same thing as 3000 microfarad. Yeah. Alright, so that's it. 3 millifarads. 3000 microfarads. Alright, so the capacitor is still fine. It's 3 millifarads. So I think I was in a hurry. I don't know if I showed you the value. Let me do it again. Alright. You're gonna zoom it a little bit so you can see it. Yeah. It's 3 millifarads. Right. So which is equivalent to 3300 because right on the body is written 3300. So if you move 3 places, 1, 2, 3, it becomes 3.3 millifarad, but it's close enough with the tolerance. Right, it's close enough. Alright, so we're gonna see if we can insert it through the board this time around. It was a little bit tough the first 2 times. Let's see if there's been any change. Alright, it's easier now. It's gone through. It's easier. So I'm just gonna put the diode there. And I'm gonna turn it back on the pin just so it's held firmly. I don't want to cut it off. It's a little bit harder now to stick it on that thing, so I'm gonna use the old style. I'll just hold it and solder the wire I'm holding it. It's gonna be a little bit harder, but let's see. Alright. And then this. So I'm gonna run a line for the ground. So both the input power supply, the 20K. Okay, I'm gonna zoom this back out so you can see where I'm showing. Yeah. So the input power supply is gonna come this way. I'm gonna run it through the 20K resistor, through the source. Yeah. Then through the capacitor, then to the output. So we're gonna just run a line there. So what I'm gonna do, I'm gonna get a piece of wire. So I'm gonna use this piece of wire to do that. So what I will normally do is I will start from one of the components. Obviously it goes without saying. And I start soldering from that point. Let me wrap it around one of the pins. Alright, so I'm gonna start from here. So solder it first. And I'm gonna resolder this one, make it firm. And then I'm just gonna run the line back. Okay. Now this one you can do the way you want. You don't have to follow my style. I just run it. You saw the diagram already, so you don't have to follow this style anymore. Do whatever works for you. Alright, so I'm gonna just run the soldering line through. Okay. Okay, the temperature is too high. I'm gonna turn it off. Because when the temperature is too high, you risk burning up the trace. The traces on the board. So I don't want to do that. I just need the temperature. I don't really need it to be on. If the temperature is high enough, then you can get what you want. Alright. So the only thing left now is the positive side, which is from the inductor. So I'm just gonna shoot that on, and I think we're done. The positive, the ground, then the output. So we can put a connector at the output to enable us to test it. So but this is the secret here. So when I fire this on, and I'm gonna program a MOSFET, an Arduino. We're gonna program an Arduino to do the test for us. And once we program it, you're gonna see the modifications we'll do with the Arduino. So the positive goes in here, the output comes in. You're gonna put low voltage here, let's say 12 volts, and we can get, yeah, that's another challenge. This 24 volts is too small. We're gonna find something else. But okay, what I'm gonna try is to do 3 volts and see if we can get up to 25 volts on the output. Yeah, but we needed a higher voltage. We needed like hundreds of volts. So I'm gonna look for a bigger capacitor to replace this. We're gonna replace this because if we test this for higher voltage than 25, we risk getting this burnt, right? So, but this is the secret. We're done with the soldering. we just need to put a power supply. So in the next episode, what we're gonna do is to program a MOSFET. Sorry, program an Arduino. Yeah, we're gonna program an Arduino and drive this system with that, and we're gonna show the effects of changing the pulse width on the Arduino. So we're gonna change the pulse width of the PWM. We'll change that on the fly and see the impact on the output voltage. And in that video, we're gonna do a little bit of tutorial to show how to calculate the voltage from the PWM. Right. So we're gonna do that in the next video. Let's not keep this one much longer. Yeah, live. Let's see how many minutes we are. We're into how many minutes now? Well, it doesn't show, but we've spent quite some time on this video. So why don't we call it a day right now? And in our next episode, we'll do the programming of the Arduino, and then also the testing. So programming of Arduino, testing, and then a little bit more tutorial and calculation of how to know the voltage you want to get. So I'll show you what you can get from 5-volt input, how you can get a much higher voltage output. So it's really amazing. It's a neat thing to do. From so little voltage you can get so much higher voltage. That's very amazing. So I'm gonna pause here. I'm gonna stop here. These tutorials, I love doing them. It takes some time, but when you see an edited video, of course it's gonna be faster, gonna be quicker. 5 minutes, we're done. We're gonna do another video, the short version, where we just show the testing and all that. So if you're the kind that like just the testing and just want to see something done, yeah, you're gonna enjoy that one, because we're gonna edit this. Or we're just gonna do a short one and we'll show that. We can even do it live, but it's just gonna be quick. Then after that, but before that, we're gonna do the full thing. We're gonna program the Arduino so we can show you that. We're already setting up for that. I'm gonna just preempt that for you, and then also preempt the next video after that. What you can see here is an Arduino. This one is Node MCU type of Arduino. You can use Arduino Nano for that. So we're gonna program that, and then with this knob here, we'll control the output voltage. You see how we go from very low voltage to very high voltage by turning this around, and we'll show you the codes from the Arduino that will help us to do that. And then we might use an Arduino Uno instead. Let me bring that so I can preempt everything for you. We've already set up on all fronts. So this is the Arduino Uno. We're gonna use the same. We're gonna do the same with Arduino Uno. We don't have to do both of them, but we've set up the Arduino Uno. We've tested this already. It's working, but it's for a different project. But you can vary it to adjust the voltage output. So that's one. And then we're gonna do this Node MCU type, and then after that, you'll be wondering what this is. This is a tuner from a VCR player, but we're gonna scavenge some components here, or we're gonna scavenge some components here in our efforts to build a TV transmitter with audio. We've built several TV transmitters, and the ones that have audio, they kind of distort the video quality. We're trying to extract some components here and use it to build a TV transmitter. Hopefully it turns out the way we're expecting. There's these components, the crystals, so we're gonna extract them to use. Let's see if it gives. Yeah, both of them, they're exactly what we're looking for. Both of them are 4.5 megahertz crystals. We're going to extract at least one of them. I think we already extracted one. We're probably going to use the one we already extracted for that. Let me see if we can find it. So there are a lot of projects coming. We've not been building projects in recent times, but we're going to do these 3 projects for you, just to show you that we haven't given up on making projects for you and with you, and encouraging you to stay enthused. That's what we want. We want you to stay enthused. Alright, so that's not what I'm looking for. Let's see, what other types of crystals, but I don't think this is the crystal I'm looking for. This is 11 megahertz crystal. No, we're looking for 4.5 megahertz crystal. What is this crystal? There's another crystal here. This is 8.46. So none of these ones we extracted already have the value we're looking for. And that's why we're gonna go scavenge for more. We're looking through our troves, our treasure troves, for crystals. We don't have 4.5 megahertz crystals. We don't. Alright, so allow me to extract that crystal, and I'm gonna build that TV transmitter. And with that, I have a TV here, color TV, that we're gonna use for that experiment. So we're gonna do that, and yeah. When we do the test, we're probably gonna use the oscilloscope here to test the waveforms of the input signal, and then also the output signal. No, the output will be DC, so there's no point. We're gonna use the digital meter to show you. We're gonna use the voltmeter to show you the output voltage, and I think that will be it. That will be it. And actually, I was surprised to see that this inductor, this toroid inductor, was up to 380. Wow. Let me measure it again. This is amazing to me. Let's just measure it one more time. This is amazing. Yeah, 386 microhenry. Amazing. And then half of it is 83. This is amazing. Okay. I'm gonna keep this inductor here. Very interesting. We're gonna use it shortly. But let's try just ordinary wire. Straight wire. These are some of the experiments I like carrying out. I need to scrape the conductor so I can expose the ends. Scrape the other side. Right, it's not properly scraped. All right, still looks like it's 0 microhenry. 0 0 0. Now, see the interesting thing about inductors. Interesting things about same wire. I'm just gonna actually leave it still connected. Let's see. When I remove it, it says overrange. When I connect it, what does it say? All right, so let's leave it connected while we just twist it on this pen. All right. Does it change anything? Nothing changes. How about if I insert a metal inside it? Nothing changes. All right. Let's wind it finely around this. I'm pretty sure if I put it on a ferrite core, the value will change drastically. All right, let's see. Nope. Let's have it. Nope. No changes. How about if I put a magnet through it? Neodymium. Let's take it easy. Nothing changes. So the values still remain very small. But that's strange that it doesn't change. That's strange. Okay. Where is my ferrite core? If I have it on a ferrite core, I'm pretty sure the value will be different, but I gotta get it on the ferrite core. Yeah, I gotta get it on the ferrite core. Okay, when I have a ferrite core, I will do the experiment, and I'll probably do it live so you can see. You can watch that live with me. But yeah, it doesn't change anything. It just means the value is too low. Alright, I will see you in the next one. Please like, share, subscribe, comment. And we're gonna finish this, and then we're gonna go ahead and build an inverter. We're working on the inverter circuit, so that'll be much later. We've built some inverters, so if you need an inverter circuit, search my channel for inverters. But what I'm trying to do now is to build a different kind of inverter. So I'm building the design from scratch. It's taking me a while, but I'm gonna get it done, and then I'll show you how to make that for yourself. As I build, you can copy. All right. God bless you, and I'll see you in our next broadcast.